So we're now going to look at two alternatives to ordinary least squares. And these are motivated by two of the problems we often find with OLS. The first of which is that if we recall the OLS formula, x transpose x inverse x transpose y, it requires us to invert a matrix x transpose x. Now in many problems we may find that x transpose x is not invertible, or it's close to being invertible, which makes it numerically unstable. This is particularly a problem if n is less than p. If n is less than p, then x transpose x is a p by p matrix of rank at most n. n is less than p, so it cannot be invertible. The matrix x transpose x is not full rank, so it cannot have an inverse. So we can't use ordinary least squares in the case where we've got more covariates than observations, i.e. when p is bigger than n. But it can happen in other cases when p is large, even if n is still bigger than p, it will still happen. The other problem with OLS that we're keen to fix is that often the prediction error, prediction variance can be large. So let's suppose we're predicting at the value of y for some new observation x. Okay. So we look at x transposed beta hat. Now the variance of this is going to be x transposed times the variance of beta hat times x. Now this variance can sometimes be large. Now if you've studied linear models before, you'll have probably seen something called the Gauss Markov Theorem. So the Gauss Markov Theorem says that ordinary least squares has minimum variance amongst all unbiased estimators of beta. Okay. So if we want beta to be beta hat to be unbiased, then OLS is the best we can do. But by abandoning the requirement to be unbiased, we can often find estimators that have smaller errors and smaller variances. So let's suppose we're estimating theta by theta bar. Okay. Then you've probably seen this formula before, but we can write the mean squared error of the estimator theta bar as the variance of theta bar plus the bias of theta bar squared. Now what the Gauss-Markov theorem says is that if this is 0, then the ordinary least squares estimator minimizes the variance. But what we're going to do now is look at some methods that are biased, that the bias is non-zero, but where we get bigger shrinkages in the variance as a result, and so we can still reduce the mean squared error of our predictions. Okay, so we're going to look at this in more detail in each section. So in this video we're going to discuss a method called Principal Component Regression, PCR. So we've seen ordinary least squares so far, and in ordinary least squares we derive the estimator of our parameter beta, and we said that what is happening under the hood, if you like, is that we're projecting our data y onto the column space of x. Or equivalently, we can think about that as projecting onto the column space of U, the matrix of left singular vectors, or onto the span of the left singular vectors U1 to UP. Now essentially what we do in principal component regression is instead project y onto the truncated set of singular left singular vectors. Okay. So project it onto the span of U1 up to UK, where K is less than P. So let's just recap. Okay. So let's say that the first K principal component scores of X are, let's call it Z which is x projected onto vk. Or we can also write this as uk sigma k, where vk, if you remember for our notation before, is just the first k right singular vectors. Okay. Or uk are the first k left singular vectors. Okay, so this is a matrix in a p by k matrix. This is an n by k matrix. So these are the principal components scores. We saw them in chapter 4. So what PCR does, PCR regresses y onto z. Okay. In other words, we have the model y is z alpha plus an error, where alpha now is a k-dimensional parameter. Okay. So instead of doing linear regression with x, we instead do linear regression with z, where z are our principal component scores. Okay. Well, let's just do ordinary least squares estimation. So the ordinary least squares estimator of alpha, well, that's just going to be z transpose z inverse z transposed y. Yep, we saw that previously. But what is z? Well, z is uk sigma k. So let's substitute that in. So that's going to give us sigma k uk transposed uk sigma k, or inverse, sigma k uk transposed y, as z is uk sigma k. Now, if we expand all this out a little bit, well, uk transpose uk is just the identity. So sigma k is sigma squared. Inverse sigma is minus 2 times sigma. So we're going to get here sigma k inverse uk transposed y. Okay. As we've got uk transposed uk its identity, they're orthonormal vectors. Okay, let's think about the fitted values again. So the fitted values for principal component regression are y hat, let's call it PCR. So that is just going to be z alpha hat here, and we use the OLS estimator of alpha. So that is z is uk sigma k. We've just found alpha hat to be sigma k inverse uk y. So this gives us, it is uk transposed y. Or if we write it out as a sum, it's the sum from I equals 1 to k of u I ui transposed y. To compare that with OLS, ordinary squares, we found the fitted values in OLS were the sum from I equals 1 up to p of ui transposed y. So it's exactly the same as before, but instead of projecting onto p singular vectors, we just project onto the first k singular vectors. So PCR projects y onto the first k left singular vectors. So the first thing to note here is that if we let k equal to p, then OLS is doing exactly the same thing, this principal component, doing exactly the same thing as principal component rejection. Okay, OLS equals PCR if K equals P. Now, although we have written this model here in terms of alpha, which is a multiple of Z, we can write Z in terms of X. So we've got that Y is Z alpha plus an error, but Z was X v K alpha. Okay. So if we think of this as beta, so our PCR estimate of beta is just VK times our estimator of alpha. Our estimator of alpha was sigma K inverse UK transposed Y. Okay. So again, this is very similar to what we found in ordinary least squares, where we found this was V sigma inverse U transposed Y. It's just in principal component regression, we have truncated matrices. So instead of using V here, we use just the first K columns of V. Instead of using U, we use just the first K columns of U. So we're just using the leading principal components, leading singular values. Okay, so why do we use PCR? Why do we use principal component regression? Well, it's to fix the problems we said before. Sometimes X transposed X is not invertible. Sometimes X transposed X is not invertible, but the PCR estimator doesn't care. We can still do PCR. Similarly, as you'll see on the example sheets, the prediction variance for PCR can be less than it is for OLS. So we can get better estimates using principal component regression sometimes than we can using ordinary least squares regression. Okay, let's look at an example now.
So let's have a look at a quick example in R. And the first thing to note is that it's really easy to do this yourself. Okay, so let's look at the iris example. In the previous section, we said we can use the linear model command, the LM command in R, to predict the sepal length and the sepal width, petal length, petal width of the iris data. Okay, so you're familiar with this, but you just do sepal length twiddles, sepal width plus petal length plus petal width, give it the data, and R will tell you the coefficients, including the intercept here. Okay, so that's ordinary least squares regression. Now, to do principal component regression, we said we're going to do linear regression on the principal component scores. So just using the first two principal component scores, we could do that as follows. So we'd start by doing principal component analysis using the PR comp command, using, remember that we just got three of the variables here, so the columns 2 to 4, the iris data, and I've scaled it. You can choose to do that or not, as suits. Okay. And then I've selected out from the rotated variables just the first two principal component scores. So column 1 and 2 of the X matrix. Okay. So that gives us the first two component scores. I'll call them Z. Then to do principal component analysis, to do principal component regression, we just do LM, the thing we're trying to predict, so that's sepal length twiddles Z. Okay, and if we do that, it gives us the coefficients. Note that I didn't center the data here, so I've got an intercept as well as the coefficients, but it's okay. R takes care of all that for us. So to convert from the principal component coefficients, so this is the coefficient of the first principal component score and the second principal component score, to convert them back to coefficients on X, the original measurements, the sepal width, the petal length and width. Okay, we just multiply by VK, we said. So if I multiply the rotation matrix, the loading matrix, the first two columns times the coefficients we found, we get these three coefficients. So 0.21, 0.38, 0.41. to compare with what we found before, they're similar but different. Okay, we don't expect them to be the same. They're going to be different because we've done a different regression model. We've got a different regression going on here. Now, we don't need to do this ourselves in R, although as I say, it is very easy to do, but we can use the PCR package, PCR command from the PLS package. Okay, so we need to install this package first. Then the syntax of this command is exactly the same as the lm command. Okay, so I've got sepal length, twiddles, sepal width, petal length, petal width. Then I've told it the number of components to consider. So I've said 2 components here. And then I've said scale it, because I scaled the moments ago, the data. And when we do that, we get the coefficients back again. And you'll see they're exactly the same as we computed. 0.21, 0.38, 0.41. Okay. So how do we choose the number of components to retain here? Well, the approach that's built in to the PLS package is using cross-validation. So we saw in the chapter on linear discriminant analysis the idea of having a test and training set. This is just a generalization of that. It splits the data up into lots of different test and training sets and evaluates the prediction accuracy on each one. So if you've done the computational statistics module, you've probably seen a bit more about cross-validation. Okay? But don't worry about it. We're just going to look at the results and pick something. So what we get out here by default when we look at the summary of the output from the PCR command, if I add in an option that says validation equals CV, gives me an estimate of the prediction error using a different number of components. So this is when I just use 1 component. This is when I use 2 components, and so Z is 2-dimensional. This is when I use 3 components. And you'll see the prediction error decreases as we use more components. Okay, and that's what we expect. But in some examples, as we decrease it more and more components, we'll see that it pays to stop adding components at some point. That in some problems, we don't want to use all the possible components. But because this is a very simple problem, there's only 3 dimensions here, we may as well use all the coefficients. It's a kind of a toy problem just to illustrate the example. Okay, so that's principal component regression.